Okay, I think we're a few minutes in now. I'm happy to start. Just checking. Cool. Okay, good morning slash good afternoon slash good evening, wherever everyone is today in the world. Uh, yeah, today I'll be actually covering the second part of the workshop on statistics, A/B testing. I believe last week it was Dr. Yassin, and he was covering some of the intro topics. Like mean, median, sampling, so on and so on. Okay, link to the notebook. So let me check because I have the link myself, but links you can download here. Okay, I see your name is JK in the chat. Last week, how was the link shared? Was it just a file, or how was the notebook shared? Was it just a file, or was it a link to a Google Colab? Okay, it was a Google Drive folder. Interesting. Unfortunately, I don't have the same folder, but I can try and make one very quickly. What I'll actually try and do as well is make a Google Colab. So I'll put the notebook there and you guys are able to access it. Let's do this. Okay, and I see some people in the chat are posting the link. Cool. And let me just double check it. Okay, so the link that was posted in the chat, and I'll post it myself so everyone has it and I'll pin it. That seems to have all the notebooks. And yes, okay, the Magnimind channel is posting it as well. So we should be good. I'll post it one more time. Okay. This will have what we're going through. So feel free to go through it. Last week, notebooks 01 and 02 were covered. Well, actually 01. And then I'll be covering what's here defined as 02 and 03. But I'll give a bit of a introduction on, I'll do a quick summary of what was covered last time and then share with you a few of the things I wanted to share in this session. Just make sure this is good. Cool, awesome. Okay, before I start though, I do want to give a bit of a intro. So if you haven't done a session with me, my name is Semi. I'm a data scientist working in the San Francisco Bay Area, Silicon Valley. I work at a company called C3 AI, and I'm a senior data scientist there. Interestingly, more on the machine learning engineering side. So a lot of just engineering, software engineering development, machine learning model development. And I haven't done A/B testing in a while. I remember preparing a good amount for it during my interviews when I finished grad school. So for context, I did my grad school in like data science and analytics at MIT before coming here. Uh, I did a lot of prep on A/B testing and statistics, but so far in my data science position, it hasn't been the case that I use it much. But I know that there are many data science positions, many of the people like that were in my program that do a ton of A/B testing. And actually, most of their job is A/B testing and statistics, essentially the core concepts we'll cover here. So it kind of goes both ways in data science. That's just the nature of the field. Can be more engineering, can be more analytics and analysis. But yeah, that's a bit of my background. And I said I'm in the Bay Area. I'm curious in the chat if people can post where in the world they're calling in from. That would be awesome. Okay, I see LA, Philly, Germany, Bay Area, Netherlands. Canada. I grew up in Canada since I was 2 in Toronto. Awesome. Okay, pretty good mix. A lot of people also in the Bay Area. That's great. You guys are very close to me. Okay, I say let's get started. And I'm gonna move this panel. This looks good. If it looks like I'm looking a bit upwards, apologize. I'm on a 2 monitor setup, and my laptop is just below the monitor I usually do my work on. Just a heads up. But okay, statistics. What are we gonna learn? What are we gonna cover? For most of the session, we're gonna cover the actual A/B testing, and we're gonna go through some experiments. And I actually want to make sure we have the chat open, so I can maybe try and answer some industry questions along the way, not just make it fully theoretical. But bear with me. Let's have the chat down here. Perfect. Okay, sorry about that. Cool. I'll try to address some core questions. Obviously, I won't be able to get to all of them, else I'll only be probably answering questions the whole session. But feel free, and if I have the time, I do want to make it a bit interactive, answer some questions, and go from there. Okay, cool. So we're gonna go deep into A/B testing, but some of you were saying that you weren't there for the previous sessions. So maybe I can give a bit of a review. Now we have these notebooks, and honestly, I think they're fantastic. They cover all the major concepts theoretically and actually give some practical examples you can go through. What is statistical hypothesis testing? Well, what is the importance of a normal distribution? I'm not going to repeat the content since, again, it's here, but it does test on these, or it does cover these fundamental concepts, right? And these are so important. This idea of a normal distribution, you're either testing from it or you're testing samples from some distribution. And then we know from central limit theorem that when you do that, okay, you know that the sample from some distribution, the distribution of the sample, it always sounds funny, the distribution of the sample is normal. And that's great, because then when it's normal, you get to do all the fun statistic with p-tests and all our p-values and all of that we know are super useful. One thing I wanted to share, so we kind of just went over, okay, this is what a normal distribution looks like. You can have the typical setup where you have mean of 0 and standard deviation of 1. Obviously, we're showing the likelihood of values and where they lie along some range. And then it's integral. The integral of this function is essentially the cumulative distribution function. Now, okay, there's a lot of interesting things here. For example, the student's t-distribution. And I really like visualizations. And I've used this website to study for my interviews that I found was super helpful. Because sometimes for me personally, I hear about the concepts and it's like, okay, sure, but I don't really understand it deeply. For example, why do we have a t-distribution instead of just using a normal distribution? Well, this website, which actually I like a lot, Our Psychologist, has a lot of these great visualizations, and you can see how the distribution shifts, and actually the t-distribution basically becomes normal, right? As you increase your degrees of freedom. The degrees of freedom, it's just number of samples. That's the easiest way to think about it, right? So if you have 14 things you're taking an average on, you're doing some computational, some statistics on it, you have 14 of them. And obviously, as you get to big numbers, it's almost exactly a normal distribution. We use the t-distribution just because, as you can see here, when you don't have many samples, your distribution, your range of values is actually a little bit fatter than the regular Gaussian distribution. All right, so all the t-distribution does is make your tail ends a little bit fatter. The reason I intuitively think of it or how I make this make sense to me is you don't have that many observations from which you're trying to take a mean from, let's say. So you're probably, if you're going to use a normal distribution assumption, you're probably underestimating the extreme value. You just don't have enough observations to really understand what is an extreme value and what is a regular typical value. Therefore, let's make the extreme tails fatter to account for that. Simple as that. And I did see a hand was raised. I'm not sure where I can see it now. Feel free to post it in the chat and I'll take a look. Post and panelists, everyone. Can I paste the URL? 100%. Cool. So that's one way to think about these distributions. Another one, critical values. Okay, maybe we can dive into that one as well. Maximum likelihood. Okay. I'm going to move this a bit to the side. I don't like that it's dark theme here, but this is another way to simulate p-values. Let's say I want to draw samples. This is great. It's exactly what our notebook is basically doing. We have examples like this. Just drawing from some existing distribution. I'm taking the mean and I'm plotting them. And I'm saying I'm going to take here n equals 5 observations in my sample. Okay. I'm going to take the mean and I'm going to plot it. So again, let's go one at a time. Oh, I took 5. Boom, my p, it landed here. And actually, I think this is saying, if you see, this landed outside my critical zone. This landed where it corresponds to a p-value of, or two-sided of 0.04. Even though we know these numbers are just coming from some distribution. This is interesting. I've actually never played with this one, but you can actually try and, if you guys are familiar with the concept of p-hacking, it's basically trying to make your statistics, your observations seem statistically significant, even if it's not. I haven't played much around with it, so I'm going to refresh it. But let me drag this around. We can also do other things like let's do z-score, same thing, draw sample, draw many, and then see where they land. And then they form some distribution down. So, okay. Hopefully playing around with this helps build some intuition. And I think one more intuition that I wanted to share. And by the way, in the notebook, we go through some super popular and useful examples of how do these statistics actually matter in the real world, right? How does hypothesis testing actually matter in the real world? It's going to be often the case that you don't have access to basically what we'd call the entire population, which I would just think of as all observations that exist for a given thing you're trying to measure. You can usually only take a sample, a small amount. So let's say in this example, we know that some electronics website is claiming that their smartphone has 7.8-hour battery life, as claimed by the manufacturer. Now, somebody is like, oh, I don't really believe that. So I'm going to grab 10 of your smartphones, and I'm going to measure their battery life. And I measured it with those 10 smartphones to be 7.6. Okay, and then we do know, let's say, that the standard deviation for battery life for the population is 0.57 hours. So maybe a bit over half an hour. Now, just looking at this could be a gauge of right now where your intuitive understanding of statistics would be. if you know that there's a standard deviation of, let's call this 0.5, and you have a difference between the known population mean and your sample mean of only 0.2, is that statistically significant? As you build up more intuition, it'll become more clear, right? You don't even have to do these calculations, that it's not. I like to visualize it through actually looking at distributions, and I'm gonna, at the end of this, show what these distributions look like. And it all, to me, is about how much they overlap. That's really what I care about. You have distribution A, distribution B, how much do they overlap? And is that significant? And then anyway, in this case, we actually go through the exact calculation where you would take you would take your sample mean. And if somebody asked a question in the chat, how do you choose the null hypothesis and alternative hypothesis? Good question. I believe it's covered up here. Just gonna scroll up to it. Okay. This is one way to think about it. Null hypothesis is basically your default assumption. This is nothing has changed. So when I'm doing an experiment, the default is nothing has changed. Basically, whatever I'm testing is not actually different, will not change anything. That's the default approach. If you want to go and jump to A/B testing, maybe I'm trying to, let's see, test a different landing page. That's always a common one. I have a landing page on my website, and I'm going to try and introduce a new one. The null hypothesis, H0, H0, is that these two things are not different at all. It's the same. The alternative hypothesis, which we can just call H1 for short, is basically saying, oh, this new landing page is actually different. And I need enough evidence basically to confirm that that's the case. And this is a good example. You can think of it in the legal system. If you've ever heard innocent until proven guilty, that's the standard for the law. And thankfully that's the case, because if it were not, law would be a mess. But thankfully we get to say everyone is innocent, you're innocent, until we have enough evidence to prove you guilty. So the alternative hypothesis is the person is guilty. And we need to build up enough evidence in the real world such that we actually reject the null hypothesis and accept the alternative hypothesis. We will only do this if there's sufficient evidence. And usually, like in law, there's a high bar. In statistics, you can quantify how much evidence you think is sufficient to basically reject your base case. Hopefully that helps. I did want to jump into one thing. Okay, I did want to finish this example, but basically you can calculate the p-value from this example and then conclude that, okay, the critical value is about 0.13. It's not significant enough to really say that this manufacturer claimed mean is not true. We don't have enough evidence. Another thing I wanted to talk about, I just wanted to quickly show one more concept before jumping to A/B testing. We can continue. Maybe there's another one. This one here. What was it in number 2? Yeah, confidence intervals. What is a confidence interval? Again, super common concept. You guys have probably heard of it, but maybe it's good to build up the intuition. You have some population, you're going to take a sample, and you want to get an idea of basically the range of where the true value is. You don't really know what the true value is. That's one really good example I actually am using at work as a data scientist, is I have some machine learning model. It's actually an LLM. And I'm trying to score the LLM and how smart is this LLM? And one way you can do that is you give it a multiple choice test. You can actually construct multiple choice questions. You give it options question and then options A, B, C, D. And then you ask it to answer with either A, B, C, or D, and you know which one is correct. Okay. I would love to know, ideally, what is the actual one number that represents the score this LLM gets on the test. But unfortunately, what you'll find is if you keep asking the LLM the same test, its score will change a little bit. Maybe one time it'll be 63%, another time it'll be 68%. So all this to say is you actually might take 10 samples, 10 tests, get the score across 10, and then compute the mean, and then add some uncertainty. So let's say I tested the LLM 10 times, its average score was 65%, but then I constructed a 95% confidence interval. So I can say, okay, 95%, basically 95% of the time, the true value will be 63% to 67%. And that just gives me an idea of where's the LLM's actual performance. It could be 63, it could be 67. It's hard to put a point estimate on it. And there's a great visualization here as well on confidence intervals. It's actually a running simulation. Let's say you know what a population mean is. Again, just to give more examples, let's say you know what the mean height of everyone in the United States is, and that's this orange line. Okay, now I don't have access to the heights of everyone in the United States. What I can do is I can take a sample of, I think it's selected here. Yeah, a sample of 5. Just pause this. I'll take a sample of 5. I will compute the mean. So let's say here, in one instance, this blue dot. And then I'll compute the 95% confidence interval. And what 95% confidence interval literally means is when I do this interval will overlap with the true value, aka this orange line, 95% of the time. What that also means is when I do this, the true value is actually not even in my confidence interval 5% of the time. And that's basically what this is showing. We've taken 104 means, and we've actually not had it in our confidence interval, these red lines, 5 times. It's not exactly 5%, but it'll eventually converge if I let this keep running. But it's interesting to think about that. You could do this and it seems like, oh, 95%, that's like basically guaranteed. Well, actually not really. You could do it 114 times and actually 9 won't even have the true mean. So I could go to my boss and say, hey, I think there's a 95% confidence interval that the height of the average US person is like 160 to 170 centimeters, when in reality it was 155. I was completely wrong. Exactly, yeah. So there's a good question in the chat. Should we expect the sample mean to approximate the true mean when sample size is increased? That's exactly the intuition to have. And it makes sense. You take more observations, you're more likely to actually represent the population. If I take one point at a time, let's say my sample was only 1. I mean, that's super uncertain. 1 person's height compared to the whole population is nothing. And you can see how wide the error bars get at just 3. Now I start making this really high. I take maybe 50 people at a time, 60 people at a time. You see how tight these error bars get now. And as you said, they're way closer to the actual mean. Now, again, it's still a 95% confidence interval, which by definition means, no pun intended, that the true value is not going to be in my confidence interval 5% of the time, as we're seeing with these red lines. But the nice thing is, hey, if I can take such a big sample, I've shrunken my error bars compared to what was there before. Great. One thing I could also do is just increase my level of confidence that I want. I think it's this. Yeah, 99. So if I want 99, you see how error bars start to shrink. Okay, my tolerance for missing the actual value goes down. So anyway, play around with this. I think it's super interesting and helps build intuition. Two-tailed tests. Okay, I think this part was fine. Okay. I think what was covered so far basically should build the fundamentals for A/B testing, which I'll go into now. Maybe since we're 30 minutes in, I mean, I'm happy to take a pause every 30 minutes and address a couple of questions. And then maybe in the meantime, some resources. Someone asked resources for practicing A/B testing questions for interviews. My best advice is YouTube. If you just go on YouTube and you search for A/B testing practice question or A/B testing practice interview question, you'll get a ton of resources. Really, really good ones too. And that's exactly what I used as well for preparing for these things when I was doing grad school. Super, super helpful. You'll find videos maybe 10, 15, 20 minutes long. People just walk you through an entire design. So I see someone's asking some industry examples for A/B testing. Because I do think that's coming up in this notebook. Heights. So there's a question for the height example. Can we use this to reason about individual new heights, or is it just for samples of multiple heights? Good question. Interesting. I haven't thought about that. So you get a height of a new person. You probably could, to be honest. I would need to dig into how you might do that. But let's say you have a sample, you have a 95% confidence interval. It's hard to say, what is the probability that this person, again, one person is part of this population. I do think that's actually the purpose of the chi-squared test. Or sorry, it's ANOVA test, not chi-squared. And that was covered. Let me just control F this. ANOVA. Okay. With one person, it's hard because it's not a sample, it's just one observation. But I think this should cover that particular question. Maybe we have multiple independent data samples. So maybe we have a sample of people's height from group A, and maybe we're not sure if they're all from AAA. Maybe one of these samples was actually taken from a different population. That's where analysis of variance test comes into place. Yeah, suggest the mean across the two groups are equal. The null hypothesis here is all sample distributions are equal. Again, they're coming from the same population distribution. Otherwise, we reject and basically say that they're not from the same distribution. And I mean, thankfully with Python, everything is just a super easy one-click function. But we can see, let's say I had some data sample 1, 2, and 3. And this one just, I'm intentionally making it different. So this does not come from the same population. I can run this. And actually the test will tell me, oh, reject. Basically, one of your samples that you gave me is likely not from the same population. And if I actually do make it the same, now you see, okay, we failed to reject. Now maybe, again, I can tweak this such that it's so slight that we will fail to reject, right? Even though I know it's different, we don't have enough statistical power to catch this, essentially. We only have 5 samples, observations per sample. Your example was something like this. Let's pretend we knew that, we had 500 people coming from one distribution And we have some other person who is, I'm just going to give them some value, say 150. I think this, oh, this needs to be a list. Sorry about that. Well, depending on what this one person's value is, we might fail to reject. Data one, shoot. Okay. Well, this has a huge difference, but I think you could run an analysis of variance. And here's the thing, okay. I'm just gonna make this random number. We'll do, this should be fine. I always forget which Python function to run, but that's fine. We'll do plus 100, and we'll do this times 50. Okay, great. And then let's look at this. Let's look at data one with plt.hist, and I have to import matplotlib. Okay, so maybe this is people's height. They're a little bit short, but so be it. And then I have my second data point, which is 150. This should fail to reject. Oh, wait, 150. Well, that's surprising. Data one, 150, different distribution. Interesting. What if I make it 100? Okay, I need to follow up on this one. Oh gosh, I'm still using the wrong thing here. Bear with me, live coding. Somehow it always finds a way to make a mistake. There we go. Okay, let's go dig into this example because I actually think it's pretty interesting. We have some sample that I took before, which I'm calling data one. I'm taking one other person and I want to actually check, is this person, this single person's height, could they be from my country? Could they be from this original country, this original population that I sampled from? And you can intuitively ask yourself, like, what would be a height that should fail, a single person's height that should fail? To me, immediately, I see like anything from 0 to almost 200, we will fail to reject, as in we can't say this person is not from the country. Up to 200, so right here, maybe we can be like, you know what, it's pretty unlikely. Since so few people from my sample are here, I'm going to reject it. And then, of course, if you go to an alien population and they're 2,000 centimeters tall, you can be like, well, this is way out of the sample mean I had before. So that's an easy rejection. Hope that helps solve that one example. Okay, one person is asking, so yeah, tests for pins versus continuous values. It actually doesn't have to do with z-tests or t-tests. You could see them the same. I mean, a proportion is still, you have events, right? Either the event is just binary, but that binary event still follows a distribution. And we can run the same tests. Really, t-test, the simplest way to think about it is your sample is small, and as well, you don't know your, let's say you might not know something like your population variance. And there's another question of, I have 5 different models and 10 questions to test each model. What type of testing can I do to choose the best model? Not trying to understand this one. I'm guessing 5 machine learning models and 10 questions to test each one. What type of testing can I do to choose the best model? I mean, best thing you could do there is again, similar to my LLM example, I'm going to pretend it's an LLM. Construct a confidence interval of each of those 5 models, those 5 LLM scores, and you'll get some ranges for each. And probably the best thing you can do, the problem is 10 questions just isn't that much. So I suspect the 95% confidence interval bars will be quite large, but run it, see where they stack up. Now, what you might see, excuse me, is that the intervals overlap. So you can't conclusively say that model A is better than model B, but that's probably the best granularity you'll be able to get to figure out which model is better. And you'll probably, assuming these models are actually quite different in their performance, you'll at least be able to eliminate some of them, I would hope. So instead of 5, maybe you have 2 that are potential contenders, and then you can construct maybe new questions to figure out which of the between those 2 models is stronger. So hopefully that helps. Okay, let's jump into A/B testing now. So this is, I know, okay, we spent maybe about half an hour covering some precursors to this. This is obviously the bread and butter of a lot of data science and analytics. Just to give the, I guess, academic run through of this, I'll cover some theory and then we'll go into some examples. All right, so you might have heard of this as split testing, otherwise known as randomized controlled trials. So always in science, this is basically the gold standard. Is it a randomized controlled experiment? And you can think about why you might want this to be the case. Medicine is probably one of the oldest and most used examples of these tests. I've developed a new medicine that I think should have some effect. Maybe one popular one would be, I think, like medicine like Ozempic right now, or drugs like Ozempic are pretty popular. Let's say you just developed it and you don't know if it works. Your null hypothesis might be, okay, taking this drug is going to not change a person's physical appearance, body fat percentage, whatever. But then my alternative hypothesis is on Ozempic, these people will experience weight loss. Okay, I can construct my experiment, exactly what levels of minimum detectable effect of weight loss and fat loss I want to be able to find. Okay, we can skip past that. How should you administer this, right? You should probably have one group of people that you select that don't use Ozempic, this new drug, and a brand new group, completely unrelated, no overlap, that you do give it to. You basically continue that for some period of time, and then you measure whatever it was that you were trying to measure. In this example, maybe you've decided that it's body fat percentage. If it's, I don't know, data science tech world, it might be like click-through rate, but let's continue with body fat percentage. And then you basically examine, okay, in my control group that didn't take Ozempic, how did their body fat percentage, how did theirs compare to the people who did take it? And you're going to try and find what the p-value is, basically what is their probability, can I reject my null hypothesis? Do I accept my alternative hypothesis that, oh, wow, it's statistically significant, this new drug is actually causing weight loss, and here are the results. So that's the simple way to think about it. In actual medicine, you do want to add a little bit more complexity. This is just another interesting example. But if you guys are familiar with the placebo effect, it's the idea that you can give somebody, or actually just the idea in a person's mind that they're taking something that gives them an effect will actually give them an effect. So what that means is, and they've studied this and they found this, it's a known scientific phenomenon, which is super interesting. But in these 2 groups, what'll actually happen is, let's say I had two completely different groups. Forget Ozempic. I had group A, who I don't give anything to, and I have group B, who I give sugar pills, just literally sugar pills. But I tell them that it's not a sugar pill. I actually tell them that this is Ozempic and it's meant to help you lose body fat percentage. What you'll find with statistical significance is that this group B actually loses body fat percentage, despite taking no substance that at least we know should do that. It's just a sugar pill. How can that be the case? The human mind is very interesting, and your belief that this effect will happen actually somehow manifests out, which just goes to show how crazy the power of your mind is, but that's a different story. So what you typically should do is actually give group A, that's why we need double blind, exactly. So what you should do is give group A sugar pills and give group B the actual pills, and then make sure what you're actually testing is that your effect is stronger than placebo. That's really what you're testing. And then there's the double blind part of it too, which is what about the doctors who administer the experiment? They themselves shouldn't know who is in group A and group B, because they will be subconsciously biased. Maybe they want a certain result. Again, they might be trying to be fair, but just the fact that they know will bias things. So the people who give them the pills also can't know who's in placebo and who's in the actual trial group. That is the most fair way to do an experiment, at least in medicine. But hopefully that just gives a bit of an overview here of why we do this. And basically what happened is tech companies got big, like Google, Facebook, they have millions of users. They're like, hey, I want to change my product, but I don't really know if people will like it or not. So maybe before I commit to a brand new landing page and hire 100 engineers to make this new feature, why don't I just run a test to figure out if people will actually like it? Now, the thing with this is we're going to go, actually, no, let's just walk through. We'll walk through how we think about this, but that's the inspiration for it. And in this example, we talk about, new UX features, new version of our product. Super common one now, we're data scientists, a lot of us, a new model. One thing for some models, like recommendation systems, you may not know how well they actually perform unless you release them in the wild. You actually give them to users. So let's say somebody has developed a new algorithm for recommendations. Maybe I'll try and do an A/B test to figure out, is that new algorithm actually getting better results? Another thing you could do this randomized control trial for. Okay. Track metrics. Again, for more details, I don't want to read through word by word, but I think everyone has access to the notebooks and they really cover in detail what is happening. Now, there's a good caveat here. And when you're doing these experiments and when you're actually preparing for interviews and when you're actually on the job, you always want to ask, do we need this? This is common for so many things. Like in machine learning, there's always a good saying that the difference between a junior engineer and a senior engineer is juniors tend to want to build the most complex thing first, some new novel thing that they read in some paper, like, okay, I want to do the most complicated thing right away. Typically, when people get more experience, like senior level, you realize that's not the best approach for many, many reasons. You really, really want to start simple. You actually want to see, do I even need machine learning in the first place? Can I solve my problem without any machine learning, right? Can I implement the most simple solution? Maybe it's just rules-based. Maybe it's just descriptive analytics. And then what you should do is say, okay, I can't, or maybe I can, but the performance is not so strong. Now I need to iterate. Is there a more sophisticated, one level more sophisticated technique that can help me out here? And then you keep going. Is there more sophisticated? And maybe at the end you get to, okay, I do need a machine learning algorithm. And then maybe after that, I need a super complicated neural network to do this with sufficient accuracy for the business objectives. But this step-by-step addition of complexity from most simple to most complicated is really one thing that will separate people from experienced and inexperienced. So just general advice there. In A/B testing, it's expensive. There's a reason we don't go most complicated first. It's expensive and we don't even know if we need it. Why would you get a Ferrari when you might just need like a Toyota Corolla? So you ask these questions as well. The product team, the engineering team, and stakeholders, can we find the answer to our business question just doing some simple analysis? Can I look at a trend? Someone has asked if we can get access to the notebooks. Let me grab it from above here. Can I pin this message? No. Okay, just resending the Dropbox or the Google Drive link. I see Emrit has something I want to get to, which is additional complexity in A/B testing. We'll get to that one, but let's give it a bit. But we want to test, just to continue on questions to ask before, do we want to test a single variant or multiple variants? You usually will test many, many variations. Because if you're going to invest the resources into doing an A/B testing, just planning it and all the execution around it, you might as well try and test various things at the same time. So maybe instead of testing my existing homepage and just one new landing page, I'll test 100 at the same time and then pick the best out of the 100. If I'm running the experiment, I might as well do that. Now, one thing we'll talk about is if you do multiple variants, you need to add some additional checks to your significance testing, but we'll get there. A big one here. Can we actually ensure truly randomized control and experimental groups such that both samples are unbiased and they actually have a true representation of the user population? Going back to the medicine example, you probably don't want group A and B with and without Ozempic to interact with each other. You don't know how that might affect their behavior. In tech, maybe one example I can try and think of, and there's many different reasons you can't make this assumption, a truly randomized experiment. Let's see. It's not exactly the same, but one good example of just general idea is if you guys are familiar with eBay, people post their items to sell. It's like an auction. At the end of the auction, the item goes to the highest bidder. Let's say I want to conduct an experiment for a new feature. This new feature will basically notify anyone who has placed a bid so far. People who have placed a bid so far, I'm going to give them a reminder 10 minutes before the auction ending to maybe redo their bid. Like, hey, person X, you bid before, just wanted to give you a heads up that the auction ends in 10 minutes in case you want to bid again. And maybe I'm thinking, can I just do an easy split A/B test? So I give some people access to this feature. Basically, some small experimental group will get access to this email reminder and the rest won't. And when you think about it and you kind of walk through the implications, you can't, because it violates the idea that they're unbiased and representative. And think about it intuitively. Getting that email is a bit of an advantage. You'll actually be more likely, let's say, I would imagine, to win the auction. So if I only give it to, let's say, 1% of people, then I run my experiment, I'm going to say, oh my God, these 1% of people, when they have access to this feature, they win the auction so much more. That's amazing. That's exactly what I want. I want people to win the auction because that's a happy customer. Well, one flaw there is, by definition, I just gave them an advantage from this test. I gave 99% of people no reminder and 1% of people a reminder. And then lo and behold, the 1% are able to actually win the auctions more because they just got a competitive advantage to let them know maybe they forgot. Oh, hey, place another bid in the next few minutes. What I would probably find is if I conclude that this feature, lifts auction purchase rate, I would probably be making a mistake because then when I give it to 100% of people, suddenly I won't see the same results. That 1% group doesn't have an advantage anymore since everyone has this feature and now everyone is reminded at the same time. So basically, we're back to status quo. No, people who have this feature, this doesn't suddenly increase bid conversion rates for the whole website. So there's one that's one example. It's not exactly there's honestly many different ways that this can be violated, but hopefully that's one. Right, so sales price might go up, but it depends what you're trying to optimize for. In my example, let's say the optimization was some type of conversion metric. There might be a flaw in this conversion metric that I'm saying will generalize to the whole population, and then I release it to everybody, and then it doesn't generalize to the whole population. There are some other ones, like in social media, network effects. If I give a feature to one group of people, but not another, there can potentially be bias because, well, one group is able to interact with the app in a different way. The other group can see this because in social media, by definition, people share. So now you've kind of interconnected these groups. They're no longer completely independent. And it goes into a lot of complexity here. I don't want to focus too much for now on that since we're just going to focus on the basics. And the basics work for many cases. Like if you get the basics down, we can add these complexities later. But that question in the chat for sales price might go up. It ties into this. What is your metric? What are you trying to A/B test for? And this is a question that will really require you to have good product intuition. Because at the end of the day, what does the business care about? They care about making profits. But if your metric in an A/B test is, does my new landing page or does my new feature or does me having, let's say I'm trying to introduce a dislike button to Facebook, not just a like button. I'm trying to introduce a dislike button. Does this impact my business profit? It's very hard to measure that with any causality. And it's also a metric that, although it's the most important to the business, will take a very long time to have any sort of conclusive results over. How long would I have to run this until maybe I see something like that? And maybe I wouldn't even see it for several quarters. So instead, what you're actually trying to do, the exact word here skips my mind, but you're trying to find a proxy metric. So you need to go through different levels. At the top, it's profit. There may be one level down for your feature, might be conversion rate. And conversion rate is a lot more sensitive to your experiment. So actually, your A/B test will reflect on this metric much more. So you'll have an easier time measuring it. And you really want an easy time measuring it because that'll make your results more conclusive. Click-through rate is always a good example. But let's say in tech companies, let's say again, in this example of I want to introduce a thumbs down button to Instagram. What is my metric? What am I trying to optimize for? And you would actually go with your product team, your product manager, other data scientists, other data analysts, and ask, what do we want from users? And typically, you might have one primary metric, but you actually might have one primary metric or even a couple, and you can take an average between them. But there's other metrics too that aren't what you're trying to optimize for, but maybe are your guardrail metrics. So let's say for this thumbs down button, I might want to verify that users, let's say there's so many, it could be they engage with more posts on average. They have a greater session time or time per session when using our app. Maybe they have more daily usage overall, so on and so on. That might be the metric you're trying to optimize for, but then the metric you're trying to guard against is maybe, let's say latency. Latency is always a common one. I don't want the app to be slower. So I want to make sure latency doesn't go up when I introduce this new feature. Maybe you also want to check deactivation rate. Maybe for some reason this makes things very toxic. And okay, great. You're getting the users who like it are staying on longer, but then you're getting a lot of people who are deactivating the app because they're unhappy now. So you want to make sure your deactivation rate doesn't go up as a cause of your test. So you take all of these into account when you're going to construct your A/B test. And in general, for that one metric, this is a good question to ask, validity question. Basically, you want to ask, like, can this one metric, this one chosen metric, increase while everything else stays consistent? If that happens, did we achieve our goal and address the problem? Simple as that to think about it. And again, we go through some common ones like click-through rate. Conversion rate is another one. Right. Similarly, I mean, we can talk about, I kind of preluded to this, the key performance indicators. Are you going to be influencing any of these negatively, positively? Maybe one example I'll just walk through. Let's say the product is to improve the quality of a recommender system and its recommendations. And maybe you can do this, for example, by adding some features to your recommendation system, like impression discounting or building a re-ranker model for the recommender. Now, the thing is, these two solutions will likely have a different impact on how they improve the quality of the recommendations. So instead, we could just decide to build a re-ranker model, which we expect to improve the quality of the target recommender. Again, this is some metric we're trying to optimize for. Let's construct our hypothesis. Okay, simple as this. I want to add an XGBoost re-ranker model to the existing recommender system recommender to increase the click-through rate of the recommendations, right? And we're going to say, what are we implying here? Higher click-through rate is good for the business. Higher click-through rate is a proxy for more happy users, more video watch time, more ad revenue, more business profit. That's how we came down to this number. And you might question, maybe this won't actually correlate in the end of the day to I see someone's leaving. No worries, it is recorded, so feel free to rewatch it. This is all recorded. If you need to drop out, you can always rewatch. The assumption that this is correlated with some positive business effect is definitely a big one. I don't know if that's always the case. And I think a lot of teams, when they conduct experimentation, there's this idea of vanity metrics. And this is so common in business because business is all about find a metric and optimize it. But what if you're optimizing the wrong metric or a meaningless metric? One great one, let's say in engineering, that a team might try to optimize is number of pull requests. Now, a pull request is how many times you committed code to the code base. If I start optimizing for number of pull requests, what I might just find happening is engineers committing lower quality code more frequently simply to make this number go up. Or instead of committing all their code in one big chunk, they actually chunk it up into little pieces so that they can have more PRs. So you need to be very, very cautious of what basically what the incentive of this metric is and how will it impact your business in the end. Okay, let's jump into designing now. We have about just under an hour left. Gresham's law. I haven't heard of it as Gresham's law, but it is. That makes a lot of sense. Give me 1 second. Have to sneeze. Okay. And this is something I want to dig into sometime. Our statistical hypothesis, we're going to have our null hypothesis and our alternate hypothesis, H0, H1. Now, when you conduct an experiment, there's actually a few things you need to account for. So we always talk about p-value, but what is p-value? It's actually not coming down here. That's your critical zone. Again, if we want to go into the exact definition, basically the probability, your p-value is the probability that you're going to observe some effect, this extreme or more extreme, right? I always just think about it as like, what is the probability that you're going to find something at the right end of the distribution here? Usually we pick 5%. So if, let's say I conduct an experiment and then the new landing page has a click-through rate that's quite far to the right of the control distribution, I'll be like, you know what, it's pretty unlikely that I would find a value under the null hypothesis. I would find a value this or more extreme, so I'm going to reject the null hypothesis. Another way to think of it, if you guys are familiar with types of errors, is type 1 and type 2 error. Let me just grab this. Type 1 and type 2 error. Let me just see if they're in here. They might have been in here. No? Okay. Very, very important to know these. Type 1 error. So the incorrect rejection of a true and null hypothesis. This is called a false positive. Basically, you rejected the null hypothesis incorrectly. Maybe you tested a landing page, you concluded that your new landing page is better, so you reject the null hypothesis, but that was actually false. It's not better. Your statistics just, you happen to fall into this error. When we say p-value of 5%, we basically mean I'm okay with making a type 1 error 5% of the time. Think about what that means. 1 in 20 times, your conclusion is actually invalid from a type, as a result of a type 1 error. That's what happens when you pick p-value of 5%, 0.05. If you, let's say, generalize this is a whole other topic, to all the papers out there that use a significance threshold of 0.05, 1 in 20 of those, at least 1 in 20 of those are actually not true. 1 in 20 of those papers are false positives. Funny to think about. Now, the flip to this is you can actually make a type 2 error. So if type 1 is you reject the null hypothesis when you shouldn't have, then type 2 is you accept, do not reject, I just say accept the null hypothesis when you shouldn't have. So actually, what does that mean? It means that new landing page in this example is better, does convert, but you weren't able to detect it. Let me just, for some reason, my camera went away. There we go. You weren't able to detect it. So you made a type 2 error. And this is called a false negative. These are the two kind of mistakes you can make in your experimentation. Okay. Someone is asking, great question, which one of these is the power of a test? Okay. That's related to your type 2 errors. So typically when you construct an experiment, you want to see how high powered it is. Power is just another way of thinking, will I be able to actually detect the effect? Another way of thinking about it is 1 minus your false negative rate. So typically, people might pick a power of 80%. In other words, they're okay with making a false negative 20% of the time. And we can read more about it here. The power of the statistical test is the probability of correctly rejecting the null hypothesis. Right? Probability of making a correct decision when the null hypothesis is indeed false. Right? You can think of it of the probability of not making a type 2 error. Okay, type 2 error is, again, you did not reject. Yeah, significance level. Okay. Just more formalized. It's good to have these formal definitions. For me personally, if you guys haven't been able to tell, I like to speak through anecdotes more and metaphors. To me, it just makes it understand. It makes it make more sense to me. But your results may vary. Right, and again, just to reiterate, we have a 5% risk of concluding with significance level of a test that there exists a significant difference when there actually is no difference. Okay, someone asked about how to choose sample size for an A/B test. Great question. The last thing I'll talk about before jumping into that is minimum detectable effect. Forget these definitions. It always confuses me. Think about it using your own intuition. If you want to let's say you're trying to detect some effect between two, your H0 null hypothesis, landing page A and landing page B. If you want to be able to make a statistically significant determination on a really small detect, let's say I want to be able to detect a change in click-through rate of 0.0001%. What does that mean you need? It probably means you need a ton of observations, right? If your default click-through rate is 5%, and you want to be able to, with significance, detect an effect of a minute little fraction of a percentage, you need to have a huge sample size to be able to separate those distributions of H0 and H1 and find that effect. On the flip side, if I just want to be able to detect something much larger, I don't need as many samples. Let's say, oh, you know what? My default click-through rate is 5%. I only want to detect something if it's 10% or more, right? Great. Well, I need way less samples to do that. Because after just a few samples, I'll know if I'm in the 10% or greater range. I'll need way more samples to know if I'm at 5.0001 or 5.0000. Hopefully that helps build some intuition there. Where should I access the recording? I think they get published to YouTube, but I'll double check with Magnimind for this. Okay, let's jump into, I think, my favorite visualization of this website, which is understanding these four variables intuitively. Okay, I'm going to solve for n. Let's look at it this way. If I set my significance level at 5% and my power at 80%, aka my type 1 error rate at 5% and my type 2 error rate at 20%. This is, and then by the way, this effect size D is that other variable. Again, just how, what is the minimum detectable effect I need? This is basically what I'm looking at. This will tell you your regions of making a type 1 error, which is this dark blue here, and a type 2. Let's go over the definitions again. Type 1. Type 1 is you reject when you should not reject. Another way of, at least, let me change this a bit. Makes it a little bit more intuitive for me. Just make it a little bit more visually appealing. The power looks good. Okay, great. Let's dig into it this way. You have some distribution of your null hypothesis, right? You can see this as a confidence interval, as a distribution. Basically, this is just representing where does your true value lie, H0. Where does your default click-through rate lie? And then now you have some experimental new landing page alternative hypothesis that has some other click-through rate distribution, represented by this blue distribution here. Where does your true value lie? And we could ask ourselves, where does if I look at this, and most people, when you look at this, you would probably say, oh, okay, there's a pretty high chance. I would probably say that, yeah, the new landing page is different and better than the existing landing page. You can just intuitively maybe determine that from looking at the distributions. What your mind is actually doing is looking at the overlap of the distributions. That's where the interesting stuff happens. Well, your mind is basically saying, let's look at type 1 error. Where in this setup, I'm allowing the type 1 error rate of 6%. You can think of this as two joint probabilities. What is the probability of, what would it be here, grabbing a value? Yeah, basically being able to, from this distribution, pick an H0 value that is greater than HA. And you'll find that that only happens on this tail, really, of the distribution. So you'd have to get very unlucky for this to happen, for this to be the case. For your true value, for your default click-through rate to actually have been on your tail here, and your true value for your new landing page to have actually been on this left tail. It's possible, but it's pretty unlikely. It's much more likely that your true value is indeed greater than your null hypothesis. So hopefully that makes sense. And you can play around with these. Let's say I have a less powered experiment. Basically, I'm accepting that I'm going to error much more frequently. I'm going to have many more cases where I don't, where I actually don't reject the null hypothesis when I should have, when I clearly I'm seeing a different effect. And then what you'll see is the smaller the effect size. By the way, we're solving for sample size. So this tells me to be able to do this, I need a sample size of at least 10.26. If I want more power, I need more samples, more sample size. If I want more significance level, same thing, more sample size, right? The more confident I want to be, the more observations I need in my sample. Same thing with effect size. Actually, for effect size, it's the flip. The smaller minimum detectable effect size, the more samples I will need. The visualization gets a bit silly here, but it's fine. We can reset zoom. If I just want to be able to detect a huge effect size, then I need way less. So hopefully that helps. Play around with this. I think it really builds an intuition. You could also determine, what you could solve for alpha. Like, hey, I can only take, maybe I can only take a sample of 100, or let's just call it 30. What alpha can I get out of this? So feel free to play around with that. I always find it super interesting. Down in this notebook, and actually I do want to take a break here. It's been at least 30 minutes since the last break. How are we feeling so far about these concepts? And maybe building an intuition and a visualization of A/B testing. Oh, apparently my version has extra content. Okay, let me do this. I'll just drag and drop the content into that drive. Okay. Okay, if not available now, I'll contact Dr. Yassine and we'll get the updated versions. But for now, let's just walk through it together. Okay, let's quickly brush through an example, and then I want to talk about some industry. Someone brought up a good example. They said, I had an interview where there were interaction effects between control and treatment. Split testing would give biased results. They asked what would be better, splitting geographically or time split. This is a ride-hailing service. Any thoughts how to design such an experiment that would provide unbiased but generalizable results? That's very common. And let's pretend it's like Uber or Lyft. Let's say I'm Uber or Lyft and I want to introduce a new feature into my app. I don't know, one simple one would be potentially paying more. Let's say I can press a button and I'm willing to pay more to get a ride right now or as soon as possible. I want to test this feature. Can I just randomly give it to some people and not others? The answer is no, because you have to be careful in marketplace environments, right? This is a two-sided marketplace. You have drivers and you have passengers. And the supply and demand dynamics, there actually are dynamic supply and demand. So if you just give in the supply and demand environment a small group of people this new feature, it's going to give them some effect. But then if you actually gave it to everybody in that group, it's kind of like the eBay example as well. You would not observe the same effect. So maybe if I gave it to a small amount of people in, let's say, San Francisco, those people would be like, oh, wow, this is great. I pressed the button to get a ride extra fast for a little bit more, and it comes. I love it. And then when I end up giving it to all of San Francisco, suddenly all of San Francisco doesn't have those same results. Why? Because now everyone has this feature. So you are competing against everyone when instead you're competing against nobody because nobody had this feature except a very small amount of people. So that's unfair. Now, whether you should split geographically or time split, honestly, I don't know what the best answer is, but I know there's resources for this online. One thing you could definitely try is geographical split. I think that one makes sense because it's probably fair to assume people in San Francisco do not interact. Like the market of San Francisco for Uber, the drivers and the passengers there do not interact at all with the market of, I don't know, Raleigh, North Carolina. There's like no interaction at all there. It's completely independent markets. So maybe doing that type of split would be interesting. But you're making some assumptions there. You're still making the assumptions that these two cities actually have similar dynamics. Maybe that's not the case. So generally what you would like to do is find these markets that are similar in characteristics, right? Exhibit similar supply and demand and usage and trend patterns. So that adds a bit of a wrinkle. Now, if you do things with a time split, that one's interesting too, but you need to, I mean, that one's actually interesting because how should you do this? No feature and then introduce the feature and then remove the feature again. You might cause people to their behavior by doing that. And you have to normalize for seasonal effects, right? Introducing a feature in February is different than introducing it in September. That's just one example. That's obviously really apparent, let's say, for e-commerce. If I introduce a feature in like November and December when everybody is shopping for the holidays, it's different than if I introduce it in January when nobody's buying. I need to factor these accounts in. Recordings. Okay, great. Recording is being posted. Okay. Again, I want to leave a lot of the theoretical breakdowns down here. But somebody asked previously if we have to treat like rates different than continuous numbers. And the short answer is like no need at all. the only thing you need to know for binary decisions, let's say again, click-through rate, it really is just derived from people either bought or they didn't. It's a 1 or 0 event. I know from just my statistics that the expected value for some binary decision is P, where P is the probability of the event happening. Let's say the event is again clicked, maybe P is 10%. Okay, so I know expectation is just equal to P. And I also know that variance, this is just from Bernoulli distributions, is P times 1 minus P. That is the variance of these binary decision events. I can go through some math and basically figure out, okay, what is the mean now, not just for one event, x1, but for all of them. Intuitively, we all know this. It's n times p. If I have a coin, heads or tails, probability of heads, p is 0.5, tails 0.5. Okay, pretty simple. If I flip this coin 10,000 times, what is my expected value of heads? You would probably say 5,000 because you're taking 10,000 flips times the single event probability p. Okay, so 0.5 times 10,000, 5,000. Very straightforward. Variance is also equally straightforward. You take your variance for one event, p times 1 minus p, and you just multiply it by the number of observations n. By the way, I was actually doing some experimentation on this while we're talking about a bit of AI. Let me do something here, ChatGPT. Guessing everyone in this chat is pretty technical. Okay, let's do this. Okay. By the way, I mean, I work with LLMs daily, so to me, maybe these things are, I hear of them faster. But OpenAI released a new model. Very interesting. This is like a new paradigm for these models. It's called O1 Preview. And it basically allows more advanced reasoning. The one question is, if you're ever confused, these tools are fantastic because these statistical concepts have been around a while. So these models know them really, really well. Can you explain Bernoulli distribution to me as a beginner? Maybe I did it, whatever. It's cool because actually now they have this idea of thinking, right? So it says, oh, the model's thinking before it gives you an answer. And then it'll pop out a fantastic example for you. You can chat back and forth with it. I always find it super, super useful. Where did my... Sorry about that. Somehow my video stopped. Okay. Another thing you could do, even with these notebooks, let's say you're like, I do not understand this at all. No problem. Go ahead and, oops, wrong button. Take a screenshot. Okay. Open up one of these tools. This one doesn't take vision, so let's just try this. What does this mean? Paste it in. And it's actually going to walk you through what this markdown means. Okay, so super useful. These tools are fantastic for learning these foundational concepts. It's exactly what we talked about. Variance, maybe it gives you some explanations. Maybe you're like, okay, this is too complicated for me. Explain it in very simple terms, blah, blah, blah. But just wanted to throw that out there because I always find it's very useful for myself. Okay. Let's skip through and talk about designing and actually running the A/B test. Honestly, that part is relatively straightforward. Once you've chosen it, let's go into, I wanted to go into an actual example, and I think, just bear with me. right? We talked about the idea of a rejection zone. Oh, let me close that. We don't need Steam notifications right now. Right, I think that was clear from going through the visualization, right? Two-sided rejection zones. I want to go into an actual example, okay? And we'll maybe cover this for the next 15, 20 minutes. Okay, and just to answer this question in the chat, how can I convert any distribution to a normal distribution? Well, one thing you can do, and what's really most common, is most of the times when you're sampling from a population, you have no idea what the distribution of that population is. So instead, what you do, and this is called the central limit theorem, you take a sample from it, take the mean, take another sample, take the mean, take another sample, take the mean, and you'll notice that the distribution of your sample means is normal. That's great. That's the fundamental theorem, like the mean of your sample means is a normal distribution. So now you can use that. You can use these samples to inform all your statistical experimentation. You don't need to know what the actual population distribution is. Well, okay, let's walk through this example together. I'll take some breaks and I want you guys to think through it yourself. Okay, so you're in charge of a website to optimize sales. You have the current version of the website, but are not happy with it. The buy now button is not obvious to the user, it's hidden away. So you want to try and make it bigger and brighter. A big, red, bright button. But you also care about statistical rigor. So you set up your website so half the people are directed to the old website and half of them are directed to the new website where you have your change. You know, and you collect data from both and you want to know, does this change, did I increase the conversion rate? I actually only care about increasing the conversion rate. I definitely do not want a landing page that decreased my conversion rate. So for me, this is a one-tail test. Again, going through common rates, we're gonna go and try and optimize the clicks on the add to cart button. This is another, again, in your interviews, you might see conversion rate, but let's say you have a product that isn't bought very often. If you use conversion rate, which is the percentage of people who actually bought, you might have a tough time measuring that and it might take a long time. There's also other effects that you'll need to keep into account, such that maybe people add to cart first, and then they come back a week later after doing some research, and then they finally buy. So how do you keep track of that marketing attribution? Just another wrinkle to keep in mind. So maybe typically you'll optimize for add to cart because it's a lot easier to track, happens more frequently. We don't need to worry about downstream attribution. Okay, now let's say this is our setup. 1,000 users, 550 were directed to site A and 450 to site B. In site A, 48 users converted, and in site B, 56 converted. Is this, simple question, is this a statistically significant result? Okay. First, we'll go through modeling this, right? It's a binary outcome. You either click a button or you did not. It's a textbook binomial distribution. And again, we have some rate for site A and B. What we can do is actually click the PMF function or determine the PMF function here for number of conversions. This is just modeling. Again, we know in, what do I want to call this? Site A, I got 48 clicks, and in site B, I got 56. So we're just basically modeling this right here and adding some confidence interval, some distribution to it, actually, because there is uncertainty. One thing here is, we can see B has an edge
B is purple in this case, actually. Perfect. B and purple. B is orange in this case. Okay, and we know it has an edge when looking at number of conversions, but it's possible that, again, if you were to randomly pick 2 points from this distribution according to their histograms, you might actually have A being greater than B. But here's the thing, we don't really care about the number of users or the total number of conversions. We care about the rates, because one thing this is not factoring in is how many people actually went to site A and site B. So let's go and talk about those distributions of click-through or at the cart rates. Right, and we can work with the binomial distributions in this case. Just the right equals 1. Okay. Honestly, just straightforward here. Going back to Bernoulli distributions, we're actually solving for, let's look at standard deviation. It's the same thing, just it's the square root of variance, and we know variance is equal to 1 minus the rate divided by the number. Okay, we times the rate again. Let's take the square root. Let's just run through this. And we know that the point estimates of click-through rate, right? If I just did 48 divided by, like, actually print these, rate A, and I print rate B. Okay, just those point numbers, 8.7% for page A, site A, and 12.4% for site B. That's what this is showing. 8.7, 12.4 with a histogram, with the actual standard deviation and uncertainty associated with that measurement. I mean, I would just ask from here. It's again going back to this visualization. For a critical value of 0.05, would you say this is significant? Would you reject the null hypothesis? Before I continue, I'm actually curious to get some answers in the chat. What do people think? Do you reject the null hypothesis or not? So I see a no. We fail to reject the null hypothesis. If you have some explanations, that would be cool too. We can just make it interactive, try and clarify any of our assumptions. So I see it depends on the variance. We have, what these are showing is implicitly the variance, right? The standard deviation. Think about what A means. A is telling you where the true value of the click-through rate for site A lands. It probably lands somewhere between 0.7 and 0.10, just to make an assumption. It probably lands between, let's say, 0.6 and 0.10. That's why we see this peak in A's distribution. But there's a chance that it's actually in these small tails. There's a chance that the true click-through rate of A is maybe 0.12. It's a low chance based on our sample, but it exists. There's a chance it's also 5%. Again, a low chance, but it exists. Now, same thing for B. Where does the true value lie? Well, there's a chance that it's probably from like 0.10 to 0.15. But it could also be 0.17. It could also be 0.7. Just the way probabilities go. So I see people saying no. And it's funny because I would have thought the same thing. My initial intuition was no, these overlap too much to actually reject. But let's go through it step by step. Okay. What is this plot showing? It's showing, given the data we collected, the probability that the actual conversion rate A and B was a certain value. Okay, and our question is still the same. This is our fundamental question. What is the probability, what is the chance that the actual click-through rate from site B is higher than the click-through rate from site A, right? So is there a chance to draw from B, okay, maybe another way of saying it. What is the chance to draw from the probability distribution of B and have that be greater than A? And is that significant? There's a nice shortcut you can do here, which is the fact that the sum or difference, basically plus or minus of distributions, is also normal, right? So if you take the difference between two distributions, that's still a normal distribution. If you take the sum, that's still a normal distribution. Okay, so when you actually calculate it, what you end up finding is this right here. My intuition. That's funny. So if we actually calculate this, right, you take the difference between the distributions. So you take your ray B minus your ray A. And then what you do here is you actually have to adjust the standard deviation or the variance. You have to add, when you take the difference between these distributions, you have to add the variances. So, okay, square the standard deviation of A, square the standard deviation of B, plot this new one. Boom. Okay, make a probability density function. And basically, this is the distribution of B minus A. What are we looking at? Another way of saying this is the distribution of B being greater than A if we draw the line at 0. And if we look at the area under this distribution, we actually see another way of thinking about this is there's a 97.1% chance that when we draw from B and when we draw from A, B is greater than A. The landing site B's conversion rate will be greater than A's. And it's interesting because looking at it this way maybe doesn't make the picture super clear. But I think what you have to keep in mind is to fail to reject the null hypothesis, you need two things to happen. You need the true value of A. You need to pick something in this zone, this far right tail, which maybe I'm just spitballing numbers here. Maybe there's a 12% chance of A being in this range based on your distribution, roughly. And not only that, you need the true value of B to also be in this left tail for the orange distribution, which also maybe is like just spitballing, eyeballing, 12%. Okay, well, each of those is 12%. You basically take the product and you get something like 3 or 4% roughly. Okay, maybe it's like 1.5%, but I'm just using rough numbers. So the probability of both of these things happening is actually quite small, which is what this shows. And the actual number is the probability of this happening is 2.9%. So really, there's a 97.1% chance that, hey, actually, yes, landing site B is better. It has better click-through rate. And let's go through this formally. So how many people are kind of surprised by their intuition after this one? And take the z-score. Are we standardizing and normalizing? Honestly, I always get confused when people say standardizing and normalizing because I always find people mix and match the definitions. It happens in machine learning too. Like normally, I think people say normalizing is when you make the range between 0 and 1. And then standardizing is when you essentially transform it to a normal distribution with a mean of 0 and a standard deviation of 1. So I'm not sure which one it is. But z-score just tells you how many standard deviations you are away from the mean. I hope that is an intuition I can give. That is what a z-score is. How many standard deviations away from the mean are you? Oh, it doesn't show z-scores, unfortunately. Yeah, well, anyway, I can't find a good visualization, but hopefully the sounds like standardizing. That makes sense. I'll accept that. Yeah, typically, I mean, normalizing, I don't think would apply in these use cases. But yeah, in the machine learning use case, it would make sense. So we would actually, again, because this is a one-tailed test, we're actually going to reject the null hypothesis and say, hey, based on what I measured, we actually have evidence that conversion rate B is better than conversion rate A. Great. Now, if this were two-tailed, we don't actually want to know if B is greater than A. We just want to know that B is different than A. So in this case, our p-value, we'd actually have to multiply it by 2. We'd have to multiply this probability by 2, because you also care about the left side of the distribution. And if we pick the same critical value of 5%, we would actually need more samples before rejecting the null hypothesis. Okay. Anyway, there's some utility functions here to calculate this, but can we check we've done the right thing? Okay. Thankfully, there's some utility function here to just calculate some of these experiments. We're using rate A and rate B. This is basically bootstrapping our results. If we know I have a rate A of this, I have standard deviation of A, right? These are results. And I'll actually do the same thing here. I can draw 1,000 samples of possible rates, and then I can figure out how many times was B greater than A, and I can run that, and I can actually validate my results. Interesting to think about it that way. Again, just taking a bootstrap here. Now, if my standard deviation were a little bit, basically, if I actually had fatter distributions because I took smaller samples in my test, let's say I add to my standard deviation 0.1 to each. Completely changes the result because the distributions are fatter now. Intuitively, this looks like this. Let's say standard deviation. I'm just going to add, oh God, I cannot type right now. Okay. Well, this, as you see, this completely changes everything. Let's make it even smaller, actually. Okay. So just adding a bit more to the variance, here the standard deviation, obviously adds more uncertainty into where the true value would lie. So if this were my actual experimental results, this is more clear. There's way too much overlap between these distributions, and we would not be able to reject. Right? In this case, area is only 86.5. Cool. Okay. I think that covers everything I wanted to. I see someone is raising their hand. Feel free to ask the question in the chat. I'm happy to answer. But this is what I wanted to cover for like traditional bread and butter A/B testing. And then there's a lot more wrinkles to this. one thing you might think of is instead of doing one landing page, what if I wanted to test, right? What if I wanted to test 100 landing pages instead of two? How does this affect my experimentation results? The actual answer here is you need to adjust your critical value, called p-value, by the number of experiments you're actually running. Why? Again, think of it in terms of a sample. If I'm willing to make a type 1 error 5% of the time in one trial, I mean, what is the probability that I'm going to make it if I do 100 different trials? If I test out instead of landing page B, I'll test out B1, B2, all the way to B100. Probably just by the nature of like sampling error, some of those will come out as being statistically significantly different, but they won't be because I just ran so many experiments. So instead, you need to adjust your p-value by the number of experiments n. So if when you just have one, what do we want to call this? One landing page is 0.05. But then when you have 100 landing pages, you actually need to adjust this by saying is equal to 0.05 divided by 100. Okay. This is your new threshold that one of the landing pages needs to be for you to say it's statistically significant. You can reject a null hypothesis. And I forget, this has a name which always slips my mind, but this adjustment does have a name. Feel free to dig into it a bit more. And right, I think from here, once you really get the hang of these more straightforward A/B tests, right? You understand this procedure, you kind of understand the statistics and intuition behind it a bit more. Then you can go into actually testing yourself with real world examples, let's say big tech companies or any tech companies, where you can't just easily separate the trial into group A and group B. We did the Lyft and Uber example as one. Yeah, Bonferroni correction, that's the one. So this is called Bonferroni correction. Bonferroni, I think it's spelled like this. There you go. Now this really just comes from seeing, knowing how to conduct your experiment when you can't just split people randomly, comes with experience. And this actually is common in machine learning too, when you're constructing a machine learning data set. The most trivial thing you can do if you want to create your train, validation, and test set is split randomly. But there's a lot of reasons you might not be able to do that in an unbiased way. For example, if there's a time component in your data, you do not want to just split randomly because you're actually, the whole difficulty in time-based data is being able to extrapolate into the future. Your model is always, when you deploy it, predicting to the future. If you start messing around and you accidentally have future data in your training set, you're going to claim that your model has better performance than it actually does. This is just like one type of data leakage. And there was another one that came to mind, but now I completely forgot. Oh, this actually applies to experiments too. How do you actually implement this? If I just have site A and site B, that when somebody clicks, let's say they Google my page and they click on semisfantasticlandingpage.com, and then on the back end, I decide, do I show them A or B? I need to make sure I don't just randomly do this on every single request. Because what'll happen is, let's say, I don't know, let's say Michael is going to my site and he visited it the first time and he sees landing page A, he leaves, he comes back, Googles it, clicks, and now he gets version B. Then I've basically corrupted and biased my groups. He's seen both versions of the landing page. I'm not actually getting a fair representation of how he would behave. So in that case, I need to actually track the users that come to my website, maybe cache their cookie, and then assign randomization by their cookie, by their user ID. Okay, so Michael always sees A. Every time he comes back, he's always going to see A. This person always sees B, and so on and so on. And so these are like the actual implementation layers you want to think of in A/B testing. Cool. And I think one more thing I can show is, let me just pop open a new tab here. YouTube. I do want to share some resources to help you actually prepare. A/B testing, data science interview. Okay. As you can see, I've actually already watched a bunch of these. Just Google things, search them up, or YouTube things. There's so many videos. Actually, this person, Emma Ding, I find has good content as well. Parse through these. And there's so many examples. And this will help build up, again, your intuition. And I think the biggest thing it gives you is a framework for dissecting these problems. Because when you actually interview, you want to make sure before you've even started, you know how you are going to dissect the problem. Because if you don't, you'll find that in the interview, you'll ramble and lose your train of thought. Use geography. Again, how you decide to split is nuanced. It really depends on the problem. This Amazon one could definitely be interesting. I think I watched it, but I don't remember. Recommend, yeah, this one's I think related to recommender systems, A/B testing recommender systems. The biggest thing I would do in your guys' shoes is when you have practice all these different ones, and then when you have an interview for a company, you know typically what the product area would be. If it's Amazon, I know I need to prepare for A/B testing related to, let's say, e-commerce. If it's Uber, I know I need to prepare for A/B testing related to ride hailing and how that is impacted by local two-sided marketplaces. TikTok, okay, I know it's social media. How do you A/B test for social media products? What considerations do you need to look at? So just try that out and you'll build your intuition there very quickly. Cool. Okay. I mean, we're basically at one. So that's really everything I wanted to share. I see Q&A in chat. Hopefully this was helpful. Again, it is recorded. I believe it's published to YouTube, and there should be more YouTube and maybe elsewhere. But I think if you follow Magnimind, that'll also be posted on their channels. Cool. Awesome. Unless there's any more questions, that's all I wanted to share. Thanks, everybody. Magnimind link is posted in the chat if you'd like to keep up. So I hope you have a good rest of your Saturday. Thank you.